right. So don't forget the spring break coming up. I know you were so close to forgetting about that, because you just want to always be in school. Anyway, so this is our last class for a couple weeks. And for today, I'm going to continue on to chapter 19. We're actually going to finish chapter 19. Chapter 19 only has...
what does it say? Please find the big one. Don't
So chapter 19 actually only has 2 sections. So we're going to finish up chapter 19 today. But like I said before, chapter 20 will use some of these same concepts. So try not to forget absolutely everything over the break. What we're doing today is we're going to be balancing equations. And at first, you might think, well, we already learned how to balance equations. Why are we doing it again? Well, let's look at this example that we have, this equation on page 689. Okay. So question, if you need to add oxygen onto this side, where are you going to add it? Every single one of our products has oxygen in it. Could you sit down and use the same brute force method that we did? Yes. Is there an easier way? Yes. Okay. So we are going to give you some techniques that will help you balance redox reactions. Okay. So we're going to start out with what is called the oxidation number method. What do you think we use in the oxidation number method?
The oxidation number?
Yeah, the oxidation number. So hopefully you did the homework and practiced a little bit with the oxidation numbers and assigning them, because we're going to be continuing to need that skill. So if we look on 689, we have 5 steps for the oxidation number method for balancing equations. So number 1, assign oxidation numbers to all chemical elements in the equation. So every single thing, all of these elements. And remember, just because the nitrogen here has 1 oxidation number doesn't always mean it's going to be the same right there. Okay. Could it be the same? Absolutely. Does it have to be? No. So we have to go through, and for every element in every compound, we have to assign an oxidation number. Okay, number 2, identify the atoms or ions that are oxidized and reduced. Okay, well, that's pretty straightforward. Okay, remember we talked about that last time. If the oxidation number goes down, it has been reduced. If the oxidation number goes up, it has been oxidized. Step 3, determine the change in oxidation number for the atoms or ions that are oxidized and for the atoms or ions that are reduced. So basically, we want to know how much did the oxidation number change? Did it go from 0 to -2? That's a change of -2. Did it go from -3 to -2? That's a change of +1. Okay? We want to see how much these are changing. 4, make the change in oxidation numbers equal in magnitude by adjusting coefficients in the equation. So we need to make the change, the total change, the same. This is because, remember, if anything is losing an electron, it has to go somewhere. And if anyone's gaining an electron, it has to come from somewhere. So we want to make the total change the same. And then 5, if necessary, finish balancing using the conventional method. Now, obviously, just hearing those words probably doesn't really explain to you how we need to go about doing this. So let's look at the example problem, which conveniently uses this equation. So the first thing that we need to do, we need to assign oxidation numbers. What's this oxidation number? 0. Why is it 0? Because it's by itself. Anything by itself is 0. All right, let's look at this. Do we have a rule for hydrogen?
Yeah.
Yeah. What is our oxidation number going to be? 3 + 1. Do you have a rule for nitrogen?
Yeah.
No.
No.
Oh.
No, we don't. Do we have a rule for oxygen?
Yeah.
Yeah. So what's this one going to be? -2. So now we can figure out that nitrogen because we know that +1 plus the oxidation number for nitrogen plus 3 times -2 equals 0. That's rule 8. Okay. This has no charge on it. So we know that the oxidation number for nitrogen has to be +5. Everyone see that? Because we have -6 + 1, which gives us -5. So that plus -5 has to equal 0. So nitrogen is +5. All right, moving forward. Now, we knew what copper was because it was by itself, but now we don't. We don't have a rule for that. So let's look at this. We're going to need to use a couple different rules. The truth is, the easiest way to do this is to consider these as ions. Okay. Because that's sort of how we have to figure it out. So this NO3, it's going to have a -1 charge. So we know that oxygen is -2. And if the whole thing is -1, once again, our nitrogen has to be +5. And then we can look at this as a whole and figure out copper, because we know we have 2 of these, 6 total of those. So that's going to be +10, it's going to be -12. But the whole thing has no charge. So in order to get the positive 10 minus 12 total, that's minus 2, but to have this plus 2. So that one's the hardest one to assign oxidation numbers of the whole thing. Okay. Everything else is pretty straightforward because once again, oxygen minus 2. But we got 2 of them, so that's minus 4. To be 0, this has to be plus 4. Here, oxygen minus 2 plus 1. All right. So now we need to look and see what has been oxidized, what has been reduced. So copper goes from 0 plus 2. So copper was oxidized. Hydrogen stays the same, plus 1, plus 1. This nitrogen, plus 5, it stays the same, but we have nitrogen here, which is plus 4. So this has gone down, it's been reduced. The nitrogen was reduced there. And then oxygen, everywhere we look, is minus 2. So it was not oxidized or reduced. Okay. So we need to figure out what is the change in magnitude. So copper went from 0 plus 2. So what is the total change? Plus 2. Nitrogen went from plus 5 to plus 4. So our total change is minus 1. What we need to do, we need to have twice as many nitrogens, right? Because that is going to give us the equal amount of total electrons moving. Okay.
Can I ask you?
Yeah.
Also, nitrogen is not plus 9 over on the right side.
This one? This one?
Yeah.
This one here? That one has to be plus 5.
So it's like underneath nitrogen plus 5 to nitrogen plus just 4, not.
So we're looking at the change. So it was plus 5 and now it's plus 4.
Oh, so we're not plus with the one up there.
Yeah, it's just this one. This one didn't participate in the oxidation and reduction.
Oh.
That's a good question. We just care about the one that participated. So it changed from plus 5 to plus 4. So in order to have, because if we look at this, what this means, okay, since copper was oxidized, it lost 2 electrons. But this nitrogen is only gaining 1 electron. So we need 2 nitrogens for every copper. So what we do, we find our nitrogens that are participating, and we put a 2 in front of them. Okay. We don't have to put a 2 right there because it was not participating. So we just put it in front of the ones that were participating. And once we have that, we go on to step 5, which is use the conventional method. We have 1 and 1. Okay, that's good so far. We have 2 and 2. We like that. We have 2 nitrogens plus 2 nitrogens. So we actually need twice as many nitrogens. So we have to change this to a 4. So now our nitrogens are balanced. Okay. Let's look at our oxygens real quick. So 4 times 3 is 12. So here we get 3 times 2, that's 6. Plus 2 times 2, that's 4. So 6 plus 4 is 10. 11. So we need one more oxygen. So we put a 2 there. So now we have 12 oxygen. And you might be thinking, oh, wait, that changes our hydrogen. It does, but we needed to change it because we changed our hydrogen there too. So now we're done. That is balanced. We can double check it. 1, 1, 4, 4, 4, 1, 2, 3, 4, 12, 6, 10, 12. The hardest part is assigning the oxidation numbers. Okay. That's just, yeah. And remember, whatever you need to, when you have the change in oxidation numbers, you need to look at it, because this one changed a total of 2, but this only changed a total of 1. The first thing we did was say, okay, we need 2 of these for every 1 of those. So we put a 2 there and a 2 there. And then once we have that, balancing the rest is actually pretty straightforward. So. Sometimes what we will do in order to work this a little bit easier, I guess, is we'll work with the net ionic equations, which basically takes out a whole bunch of stuff that what we call spectator ions, things that are there but don't really participate. For example, with this, so we can see, okay, so we've got this nitric acid. So we know that this is happening in an acid solution. Now, nitric acid is a strong acid. And look, you can see NO3 right there. Okay. So a bunch of these aren't really going to do anything at all. Some of them will. But since it's a strong acid, we can say we have copper plus H plus NO3 minus. Because remember, strong acids, they completely break apart like that. So once we're in solution, this is actually what we're dealing with. Same thing with this copper nitrate. Okay? It is an ionic compound. So we can say we have copper, and then we have the nitrate ion. This right here, it's not an ionic compound, so we have to keep it just the way it is. And then we have water. So at this point, what we can do is we can actually get rid of all of these things that don't actually participate. So any of these that the number is the same on both sides, we can just get rid of them. So obviously, copper and our nitrogen we need to keep, but hydrogen stays the same. So we can get rid of it. So we just have copper and our nitrate. And then on the other side, well, once again, water is the same. We need our copper there. This, because it's the same as that. Now, some of these didn't do anything, so we don't worry about those. We have that. Okay, so that is our net ionic. We do want to make a note that this is an acid, because then we know that we took out these things. So sometimes you will see it like this instead of like that. Okay. If you're given this, it is, to balance it is pretty much the same as the oxidation number method. It's a little bit easier to assign these oxidation numbers, and that's why sometimes we do it. Once again, 0, NO3, so this is going to be +5 minus 2. This is going to be +2. And then we have +4 minus 2. And we do the same thing. So this has a net change of 2. This has a net change of -1. So if we put 2 right there, 2 right there, it becomes a little bit easier. And then all we have to do is basically add back in the rest of it. So I'll be honest, I don't love the oxidation number method. It is useful, but I actually prefer doing this other method, which is called half reactions. So let's look at that. Now, I prefer it. That doesn't mean you will. On your homework, you're going to have to do both. But, yeah. Anyway. So the half reaction, we've brought up the concept of half reactions before. And it's basically dealing with either the part that's being oxidized only or the part that's being reduced only. I think that's why I like it, because you only deal with one half at a time. So you don't have to look at the entire reaction. You're just looking at part of it. So, once again, we have a list of rules. Write the unbalanced net ionic equation for the reaction emitting spectator ions. So the first thing we do, we get rid of anything that is not being oxidized or reduced. That's what we did with that other one. Okay. Write separate incomplete equations for the oxidation and reduction half reactions. Balance the atoms in the half reactions. Balance the charges in each half reaction by adding electrons as reactants or products. Adjust the coefficient so that the number of electrons lost in oxidation equals the number of electrons gained in reduction. Add the half reactions, cancel or reduce like terms on both sides. Return spectator ions if desired. So, now, we're going to go through example problem 5. I'm going to tell you right now, example problem 5, basically they chose it as an example because it shows everything. Okay? The problems that you will see, especially on tests, are not going to be as complicated as this example problem. Okay. So I just want to warn you ahead of time. Okay. This might seem like there's a whole lot going on, and it's because there is. But the problems that you are going to be expected to do will not have quite this much going on. Okay. So we'll do example problem 5, but then we'll also do one of the practice problems together to show you a little bit more what you should expect. All right, so it gives us this equation. So right off the bat, you can tell there's a lot going on. We have 7 different things. Okay. So we need to figure out what is what is basically our oxidation and reduction. Okay. We need to get rid of everything that is not participating. Well, to do that, to really do that, we need to assign oxidation numbers. Okay. So potassium +1, that's a rule. We don't have a rule for manganese, but we do have a rule for oxygen, -2. So we've got 4 of these. So we have -8, we have +1. Total thing has to go to 0. This is +7. Our tin chloride. Okay. So chlorine is going to be -1 because it is more electronegative. We have 2 of those, so that has to be +2. Here we have -1 +1. -1 +2. -1 +4. -2 +1. -1 +1. So now we want to only keep those things that are changing. Potassium, it's the same. MnO4, yeah, we need to deal with this. Okay. Tin, that is also changing. But this is actually ionic, so we're just going to deal with this. Write that backwards. Here, nothing's changing. So now we say, okay, we need our manganese. Once again, this is an ionic one, so we're going to get rid of chlorine. And this is going to be plus again. Ionic, so we're going to get rid of it. And this one is going to be 1. Oh, my goodness. So the water, potassium chloride, that's all the same. So this is a lot less to deal with, right? Okay. So we are going to, we're going to break this into its 2 halves. Okay. Okay. And so now we just want to deal with one at a time. We're going to start with the tin because that one's easier. So we look and we say, okay, we have 1 tin, 1 atom of tin. So that is good. We don't need to change how many atoms we have. But the total charge on this side, +2, total charge on this side is only +1. So remember, when we're dealing with redox, we can use electrons to balance the charge. Okay. So we take whichever side is the higher number. This is +2, +1. We're going to add electrons until they equal out. Well, we only need one. Okay. We only need one electron. I've done something wrong. This is 4. Oh, wow. Can you tell that I'm ready for break 2? I've erased so many things because, yeah, wow. Okay. So this is actually 4+. There we go. That's going to make things work out. Okay, if we get the charges correct. So, because we have 4 of those at -1, so that means that has to be +4. We'll get there. So we actually need to add electrons to the other side. That's what was throwing me off. I was like, the electrons shouldn't be there. So we actually need to add 2 electrons here. Okay. All right. So we add these electrons. And now that's done. Our tin is done. Now we need to deal with this one. Now this one is a little bit more complicated, but it's not too bad. So first we need to make sure that the atoms cancel out. Okay. So we have 1 manganese on both sides. But this side has 4 oxygens. The other side doesn't have any oxygens. How can we solve that? Can we solve that by remembering this is happening in water? So if we have 4 oxygens, we can add 4 water molecules. So now we have 1, 1, 4, 4. Dang it. We added hydrogen, didn't we? So how do we solve that? We are in acidic conditions. What is acid? H+. So we can add 8 H+. So now we have 8, 8, 1, 1, 4, 4. That's what I was looking. So now we have the atoms themselves balanced. And so now we look at the charge. We have a 2+ charge here and 0 right there. So we add +2 and 0 and we get +2. Here we have 8+ and 1-. So +8 plus -1 is +7. Okay. So we need to get these equal. We need to get +7 down to +2. So how many electrons do we need to add? Yeah, 5. Don't overthink things. Okay. How do you get from +7 to +2? You subtract 5. So we need to add 5 electrons. Okay. So now both of our half reactions are balanced. Now we got to put them back together. But we need our electrons to cancel out. Because remember, anytime you're losing one, it goes somewhere. Anytime you're gaining one, it had to come from somewhere. So our electrons have to cancel out. So what we have to do is multiply these entire half reactions by a number that's going to get our electrons to cancel out. And as it turns out, we have to multiply this one by 2 and this one by 5 because we need to have 10 electrons on both sides. Okay. So what we end up having, so we're going to multiply all the coefficients by 2. So this one becomes 10. This becomes 16. This didn't have one, so we can put a 2 right there. Same thing here. And this becomes 8. This one we're multiplying everything by 5. We get 5, 5, and 10. So now we add these together. So we have 10 electrons plus 16H plus 2 NO4 minus plus 5, 10. We add everything over here. And now we need to cancel stuff out. So these electrons cancel out. Sometimes you will have waters and H plus on both sides that you have to cancel out. This one, it doesn't happen to have that because this was such a simple half reaction. So at this point, since we started with all of our spectator ions, we can add them back in. So where do these 8 plus comes from? Right here. So if we have 16 HCl plus this came from right there. The tin right there. So we have 1, 2, 3, 1, 2, 3. Good. This ion came from right there. The water, well, it actually just came from right there. And this tin came from right there. And if you notice, that wasn't anywhere. So we have to put that in. And now, because we had to put one thing back in, we just have to double check, make sure everything is still balanced. So our hydrogens, we've got 16 here, we've got 16 there. Our potassium, we've got 2 here, we only got 1 there. Let's put 2 there. Manganese, 2, 2. Oxygen, 8, 8. 5, 5. Chlorine, so we've got 10. We've got 4 there. Oh, sorry. There's 26. I forgot about that one there. So we've got 10 plus 16. So we have 26. So we've got 4 plus another 20 plus 2. So, like I said, that one is we're going to show you absolutely everything that you could ever possibly need to know about doing this. Okay. Like I said, we're going to do an example problem together, which is going to be a little bit more like what you would expect to see, say, on a test. Okay. So let's look at Let's look at 23. So 23 gives us this equation. Right away, you should be able to see that this is a little bit different because this is actually our net ionic reaction. Okay. It does tell us this is in acid. Okay. So since it's our net ionic reaction, we don't have to get rid of any of our spectator ions. Okay. We don't have to get rid of any of them. Honestly, when I have this, if I'm given the ionic reaction, I completely skip the step of doing oxidation numbers because I can already see where I have to split things. Pretty straightforward. Okay. Once again, I would start with this one because it's simpler. So we have this diatomic iodine. We need two of them. Okay. So we need two iodines, two iodines. Charge on this side is 0. Charge on this side, because we have 2 at -1, is -2. So we add 2 electrons. Then we can come back up to our chromium here. So we have 2 chromiums. So we need to put a 2 right there. 7 oxygen. Remember, we're doing this in acid solution. So we add 7 waters across from the oxygen. That introduces hydrogen into the mix. But since we're in acid, we can add 14 H plus over here. So now, double check. So we have 14, 14, 2, 2, 7, 7. So once we have that done, we look at our charges. Now, right away, I know if I'm doing things correctly, I'm going to have to add electrons over here because I added them as a product for the other reaction. So once again, we have 2 at 3 plus, so this is a total of 6, positive 6. This is a total of 0. 6 plus 0 is 6. So on the other side, 14, negative 2, so we have 12. So the difference between positive 6 and positive 12, 6. So we need to add 6 electrons. So now we need to get them to the point where when we add them together, the electrons cancel out. This one is also easier than the previous one because we only have to multiply one of the half reactions. If we multiply this by 3, there we go. So now, 6 electrons, 6 electrons. Once again, as with just about everything in this class, as you get more comfortable, you can do more steps in your head. When I'm doing this, I say, okay, I know that these electrons are going to cancel out, so I just don't even bother with them after I add them together. And then we do 14 hydrogen. We've added it together. Now we can double check. 14 hydrogen, 14 hydrogen. 2, 2, 7, 7, 6, 6. As far as the charges, positive 6, 0, 0. So over here is positive 6. Here we have 14 positive, minus 2, which brings it down to 12, minus another 6, brings it down to 6. It didn't give us any spectator ions, so we have nothing left to put back in, and we are finished. So that one seems much nicer than the first example problem, right? Yeah. So that's more on the level of what you should expect, especially for a test. Now, sometimes you might have to do something where instead of being in acid, it's in basic conditions. It is possible to work with OH minus here instead of H plus. For me personally, I find it easier to completely do it in acid until we get to this point. And then you just realize, well, anytime we have an H plus in basic conditions, it's going to react with OH minus. So anytime we have this right here, this H plus, what we're going to do is we're going to change this. We're going to react it with OH minus, turn it into water. But in order to keep things balanced, we add however many OH minuses that were there. And then we can cancel stuff out because we have 7 waters here and 14 here. We do that. So at the end, let's clean it up. We'll have 7 water. This is going to be gone, and then we'll just put that in its place. And now we can once again double check our work. 14 hydrogens, 14 hydrogens. 7 plus 7 oxygens is 14, which we have right there. 2, we already did oxygen. 6, 6. The charge on this side is -8. Charge on this side, so we have 6 plus -14, which is -8. And this is now in basic conditions instead of acidic. So, anyway. So this entire section was just about balancing equations. We've got the oxidation number method, where we take the difference between the oxidation and the reduction, the total magnitude, equal those, finish the rest. Or the half reaction, where we split it, balance each one independently using electrons, water, and H plus, and then put them back together. Or if it's in basic, Like I said, I find it easiest to just use H plus the whole way, and then just at the end, react all of your H plus with OH minus, and put that many OH minuses on the other side. Questions? Okay. Well, let's do some homework. Okay. Go ahead and get started with that.